Welcome back, everybody. Last time we asked the question, how does the fundamental theorem of calculus generalize to higher dimensions? And we saw our first way that it did, right? Instead of integrating f prime over an interval, we saw that, well, for integrating the gradient of a function over a curve, the result is the same as before we get the net change in f, right? Just f of the endpoint minus f of the start point of our curve, right? And so here our curve is parameterized in some direction here. All right, so just like with FTC2, we get the net change in f as the value of our integral. And because of this fact that the value of the integral only depends on the endpoint and start point of our curve and does not see anything in between, really, we saw that gradient fields are independent of path, right? It doesn't matter what path we take from our starting point to our endpoint. The FTLI says that we'll get the same result, right? It's the net change in f. We also, at the end of the lecture, mentioned that gradient fields are the only vector fields with this property. And because of that, because of this nice property that gradient fields have, a natural question is, well, how can we take our vector field that's maybe just handed to us and see if it actually is a gradient field? And this is the question that we're going to be thinking about today. And it turns out that there are really two ways to go about this. One is an indirect way, where we can somehow tell if it's a gradient field, but we don't necessarily know the little function f, whose gradient is our vector field. And the second is a direct way, where we just kind of put on our work gloves and try and find this function, little f. All right, let's start talking about these, and we're going to focus first on the indirect method. And the result here below gives us our answer, and essentially the indirect method is to check the cross partials of our vector field. And so this theorem says that, well, here if we have a vector field here on the xy plane, this vector field is conservative, right? In other words, it is a gradient field if and only if the partial py equals the partial qx. And so I want to make a couple of notes about this. For starters, I use the phrase cross partials here because I know p is the x component of our vector field, and so the partial py I think of as like this x component's partial with respect to y, and similarly qx, that's this y's component's partial with respect to x. And so I kind of see these kind of crisscrossing arrows in my head when I write this equation. That's why I call it a quality of cross partials. X component with respect to y, y component with respect to x. The next thing I want to mention is that there are some niceness assumptions that do go into this result. And we're not going to really worry about the details, but I do want to take this opportunity to introduce some terminology here. The result asks that this equality of cross partials holds on a certain kind of nice region, specifically an open, simply connected region. And we've seen this word open before, right? Open just means we do not include the boundary of our object, so no boundary. Connected means just what it sounds like, just means that there is one piece. The simply portion, that says not only is our region one piece, but there's actually no holes or anything in our region. And so to draw a picture, the kind of region we're thinking about looks like this. So no boundary, so I'll draw this dashed. And then everything inside is just filled in completely, right? So this sort of region, this is an open, simply connected region, whereas if we did something like this, no boundary, but maybe we kind of plucked out a hole and made sort of a donut type region. This is open and connected, yes, but not simply connected. All right, and so this is, this is the kind of region we're thinking about, this equality of cross partials holding on. The next and last note I want to make about this is that we can actually see one direction quickly using some results that we talked about before. So for example, let's say that our vector field is conservative. I claim that it's quick to see that these cross partials are going to match, and this is the left to right direction of this result. All right, so the idea here is, well, if our vector field is actually a gradient field, well then we know what our components P and Q are, right? They're just the partials of F. Well then, if that's true, well then think about what our cross partials then are going to be. Right, our first cross partial is Fx with respect to y, and our second cross partial is Fy with respect to x. That's right here. And notice what we're ending up with are just these mixed partials that we've seen before and talked about. These are going to be equal. And so, yes, if our vector field is a gradient field, then these cross partials are going to match. It's going the other direction that requires more heavy machinery. But it is true, and this will be our indirect check. And so, for example, if we just get handed a vector field here, we can ask, is it conservative? Well, we can go ahead and check the cross partials. And if you haven't done that yet, go ahead and pause the video and take just a minute and see what you get. All right. Well, let's see what we get here. Right, we have our x and y components, and we want to take the x components partial with respect to y and the y components partial with respect to x, and we're going to get negative 4y for the partial on the left with respect to y. And over here, if we take the component on the right's partial with respect to x, we're going to end up with just 4y. And it's as clean as noticing that these are not the exact same, right? This one has a negative. And so because these cross partials do not match up, we can say definitively that our vector field is not conservative. It's not a gradient field. So before moving on to our direct method, let me mention that this indirect test of cross partials does generalize nicely to higher dimensions, to vector fields on 3 space, even 4 space and beyond. Let's just talk about 3 space. It turns out the result is that our vector field is conservative if and only if just all of our cross partials are equal. Again, there is some niceness assumption on the region and all that, but we're not going to worry about it. And so what I mean by all cross partials is, well, here we have an x, y, and z component now. And we just need to pick 2 of these, and for each choice of 2, we get a cross partial. All right, so if we choose x and y, we get this cross partial to think about. If we choose y and z, we get this cross partial to think about, right? The partial of our y component with respect to z needs to equal the partial of our z component with respect to y. And lastly, if we choose x and z, then we have this cross partial that needs to be equal. And so we have the same check of just checking all of our cross partials, making sure that they're equal, to see if a vector field on 3 space is conservative. Right? If any one of those broke and was not matching, we'd be able to say that our vector field is not conservative, that it's not a gradient field. All right, let's move on and think about our direct method. And so here, we're just going to straight up try to build our function little f, right, with the gradient of that function actually equaling our vector field, and we'll see how it goes. And so here, we're just going to dive in and see how this looks with an example. So here's a vector field. It's on the xy plane. We can see since it has just 2 components. Let's try to find our little f potential function, right? That's the language for our little f, such that the gradient of that function is our vector field. And the idea to get us started, that really is the engine behind this method, is, well, if such a function exists, and the gradient of that function equals our vector field, well then we know what the 2 components of our vector field equal. Right? Thinking about how gradient fields work. Right? The x component is fx, and the y component is fy. Right? So if there is such a function little f, well then we know exactly what its 2 partial derivatives are. And we can kind of one at a time look to use this information and try and back up and see what our function f would have to look like. All right, so looking at the x component, back up, we know that 3 plus 2xy would have to equal fx. And so if that is the partial with respect to x of our function f, well then, backing up, in other words, integrating with respect to x, well, our function little f would need, thinking about this 3, it would need to have a 3x term. And looking at the 2xy, anti-differentiating that, we would need a x squared y term. All right, next, looking at our y component, we know that fy would have to equal x squared minus 3y squared. And again, backing up, integrating with respect to y, if we look at x squared, well, integrating that with respect to y, we would just need to multiply that by y, right, since this is a constant with respect to y. And so we get an x squared y. And then our last term over here, the 3y squared, integrating with respect to y, we would need a y cubed. And so through this information that our two partials would give us, we can piece together our function. And notice that two of these pieces of information match up, right? From fx, we saw that our function needed x squared y, and from fy, we also saw that our function needs x squared y. All that tells us is that our function needs x squared y. We only need to include it once. We don't need like a 2x squared y or anything like that. We just need to include that term x squared y. They're just both telling us the same thing. All right, so putting these pieces together, the 3x, x squared y, and the minus y cubed, here now is our candidate for our little f function. At this point, to check if this really works and this is indeed the function whose gradient is our vector field, we just need to actually compute our partials and essentially find the gradient field of this function. And so working through that here, the partial of our function with respect to x is going to be 3 plus 2xy minus 0. And then the partial of our function with respect to y is going to be 0 plus x squared minus 3y squared. And if we compare these to the x and y components of our vector field, we see indeed that our function little f's gradient is equal to our vector field, and directly we have thus shown that our vector field is a gradient field. Now it's possible for this process to kind of go wrong, and show us that our vector field is not a gradient field. And how that could happen is in the check. So I have a quick example here to show how that looks. So for example, if we had the vector field 3x, right, to go through this, this direct method, we would say, okay, well, if such an f exists, then this 3, right, that would be our fx, and this x, that would be our fy. And so looking at the x component information, our function would need 3x. And looking at the y component information, our function f would need xy. And so putting those together, our candidate function is this function right here. And if we do our check, well, partial with respect to x is 3 plus y, which notice already we can see doesn't match. And so already we can see that, okay, our vector field is not a gradient field. Right? If we wanted to, we could do our second check as well. Take the partial with respect to y, and in this case, this one actually does match. But our partial with respect to x does not, and so we can say that our vector field is not a gradient field from that work. We could also use our indirect test real quick to check the cross partials and see that they don't match up. But this is how it looks for this direct method to communicate that the vector field we're working with is not a gradient field. All right, so a quick summary of these two methods, right? Our indirect method is to check the equality of our cross partials. And our direct method is just by using the information that we can get from our x component, our y component, and if we have one, a z component, right? Through anti-differentiating, see what we would need to have a little f function whose gradient is our vector field, and then check it out afterwards. And somehow, in terms of integration, the point of all this is that, well, if we're integrating, some vector field, if we're doing a line integral of a vector field, well, if our vector field actually is a gradient field somehow in disguise, well, if we can figure out this function little f and kind of see our vector field as a gradient field, well, then the fundamental theorem of line integrals is so much cleaner to use than our standard, parameterize our curve and translate our integral process that we use just for computing line integrals and line integrals for vector fields in general, right? If we have a gradient field, then life is good, and that computation goes very cleanly using the fundamental theorem. And so with that idea in mind, let's take a look at our last example for the day. So here, let's use the fundamental theorem for line integrals to compute the line integral for a vector field, where our vector field is this one right here. So 3 components, so we're a vector field on 3 space. And the curve we're using isn't really specified. We just have some curve starting from this point and going to this point over here. And let me just mention real quick this language of use the fundamental theorem or line integrals to compute this. Right? The fundamental theorem for line integrals is a statement about line integrals for gradient fields. And so what's implied in this language is the fact that our vector field here is actually a gradient field. Right? It's the gradient field for some function little f. And so if we want to use the fundamental theorem to compute this line integral, well, then we just need to find that function little f. So at this point, pause the video, see if you can take our vector field here, and by considering the x, y, and z components, try and construct our function little f and check it out, and then use the fundamental theorem to compute our line integral. All right, so let's talk about this one here. So if we're going to try and find our function f, whose gradient is our vector field, right here we're doing the direct method, just trying to kind of by hand construct this function, right? And again, the idea is that, well, if there is such a function little f, well then we know it's 3 partials just by looking at the components of our vector field. All right, so looking at our x component, if that's the partial with respect to x, well then backing up, right, integrating with respect to x, this one's a little bit awkward to see. Notice the only place where the x is up here in the exponent. And so we're definitely going to need that exponential piece, e to the xz. But if it was just that, then taking the derivative with respect to x, we get e to the xz times z. And we like the e to the xz, and we like the z, but we also need that y. And so we'll scale that in. And so here's what our function f is going to need, looking at our fx information. Looking at our fy information, well here, this is actually a constant with respect to y. And so integrating, we just multiply by a y. So this is what our function is going to need. And lastly, looking at our z information, similar to our x considerations here, just walking through that, our function f is going to need y times e to the xz. Again, the idea is, well, if it was just e to the xz, the derivative is e to the xz times x. Now, since z is our variable, and we like that, we like the e to the xz and the x, but we also need that y. So actually, in this case, all three of our components are telling us the exact same thing. And so from that, we get our candidate for our function f. And so we just need to go through and take this thing's partials to check it out. And with respect to x, again, we have that y just hanging out as a constant multiple. The exponential stays, and then for the chain rule, the derivative of the exponent is going to be z. And we compare that to our x component here, and yes, that checks out. Next, partial with respect to y of f, the y just goes away, e to the xz, and comparing that with our y component, that checks out. And lastly, partial of f with respect to z, and the y hangs out as a constant multiple, then differentiating the exponential, we get the exponential times the derivative of xz with respect to z, which is x, and comparing that to our z component. That checks out as well. And so with that, we have found a bona fide potential function f whose gradient is our vector field. And so with that, right, the line integral that we are wanting to compute over our vector field f, well, our vector field f, it equals the gradient of our function little f here. And at this point, right here, this is a line integral that the FTLI speaks to. The fundamental theorem for line integrals tells us how to compute, right? The fundamental theorem tells us that this integral just equals the net change in our function. Right, and so here our curve started at 1, -1, 0 and ended at 5, 3, 0. So we just need to take those points and plug them into our function. Doing that, we'll get, I guess, what? For 5, 3, 0, we'll get 3 and then e to the 0, which is 1. And plugging in 1, -1, 0, we'll get -1 out front. And again, e to the 0. So putting all that together, what do we get? So 3 times 1 plus 1, which equals 4. All right, and that's how it can look to take a line integral and take our general vector field and try and find the function little f whose gradient is our vector field so that we can use the fundamental theorem to compute our line integral. Good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.